So today we have Yousef Kimiagar, who's an accomplished management and technology executive with over 30 years of experience at senior levels in organizations and management roles in multi-billion-dollar rail and transit projects. He's currently Vice President of Transit Rail Systems and responsible for the Canada region with Fleming Consulting Group. He has a Master's in Management Science from the University of Waterloo and a Bachelor's of Science in Electrical Engineering from IUST, and an executive certificate in Artificial Intelligence Implications for Business Strategies from MIT. He's a professional engineer in Ontario and BC and a project management professor and fellow of the IRSE organization in the UK.
Thanks for the introduction, and good afternoon, everyone. The rail industry is playing a major role in today's economy, but it is facing its own challenges. And today we'll just try to see what those challenges are and how advanced train control systems are helping to overcome some of these challenges. For a moment, let me take you back to a Friday afternoon, a sunny Friday in California, September 12, 2008. There is a concept in the rail industry that we call it single track. For whatever reason, there are areas that we cannot have dedicated tracks for each direction, and we have to operate bi-directional on a single track. As you can see here, Union Pacific Freight Rail is operating on permissive signal in the direction of the arrow, and at the same time, Metrolink passenger train is moving out of the double track and getting into the single track. There are signals in these cases that the drivers must follow for safe operation. But in this case, similar to 80% of all the train accidents, the driver passes the signal at danger. That means that it passes the red signal and enters into the single track. And then you know what happens. Tragedy hits. The passenger train with over 220 passengers on board collided head-on with the Union Pacific freight train. In this accident, 25 people were dead. 135 people were injured, many of them severely injured, some of them disabled for life. So, this is the challenge, one of the major challenges that the rail industry is facing. Human errors and the lack of sufficient infrastructure. Let's just take a global view on the rail industry, the population growth, and the growth in the ridership, because it is just the exacerbating the impacts on the rail industry. The population is growing. By 2030, the world population will be 8 billion. But at the same time, the population of the urban cities are increasing substantially. So that's adding up to the challenges. Back in 2010, around 2010, the population of the urban cities exceeded the rural areas. So that means that it is just putting more challenge on the urban cities for the passenger transportation, at the same time for shipping and receiving goods to those people who have migrated from rural areas urban cities. The total ridership as of the end of last year globally was over 53 billion per year. And as you can see, it's trending upward. What is important is the infrastructure catching up with this increased load? Possibly not. So that means that it just adds up to the pressure on the operators in order to move more passengers throughout their systems. And that's where the system becomes overloaded. Taking a look at the top 10 cities in the world, which have the highest ridership. Let's just take a look at the stations, how they are loaded. This is Tokyo, the #1 city in the world with the highest ridership. Hong Kong, it's a similar situation. Beijing, it also has a similar case. In fact, sometimes the passengers on the train cannot exit the train because the passengers on the platform will not let them just to exit and push them back in. Paris, same thing. Moscow. New York, one of the oldest infrastructure in North America and in the world, and it's just facing a lot of challenges. London tube lines. And finally, Toronto. Although Toronto is not part of the top 10 cities in the world, but I include it because it is our hometown, and we better just know what is happening here. If you just put the entire ridership into charts, that's what it looks like. The size of the bubble represents the ridership, and the elevation on the chart shows the length of the network. So as you can see, Tokyo, with over 3.4 billion riders per year, has a network around 400 kilometers, and is the #1 in the world. On this chart, you see Hong Kong, the lowest ridership of 1.6 billion per year, has a network of around 170 kilometers. So this is the way that the total ridership in the world, top 10 cities, look like. Now, if you want to just go further down and drill into this information, we come to another chart. This is the throughput, which shows the number of passengers that the rail system, the transit system, moves per kilometer of their network. So here you see again, Tokyo has the highest throughput with 9.1 billion passengers per year per kilometer of the network. What is interesting here is that Hong Kong, which used to be 10th on the ridership, now is climbing to rank 4 for the throughput. So how these cities are overcoming these challenges? Well, obviously, this is not the way that they are doing it, although Tokyo is having some station attendants in order just to push passengers to the trains so that the trains can move on time. But train control systems are the #1 reasons that the throughput in the systems can be increased. And here we just look at some of the key train control systems that are widely adopted globally. The goal of the train control system is to protect the passengers, to protect the trains from collisions. If you just look at some of the key functions, critical function of the system is determining the train location, determining the speed that the trains are traveling, the direction they are traveling, separating them safely and stopping them based on the safe braking model, and then protecting them from derailment and not over-exceeding the speed. At the same time, we see that there are level crossings, that the trains are crossing the intersections, so protecting the trains from colliding with the road traffic and overall collision avoidance. So these are the key functions that a train control system has to deliver. Automatic train control system, which we call it ATC, it has many functions. The functions can be grouped into 3 main categories. The first category is ATP, automatic train protection, which is responsible for protecting trains from against collision, excessive speed, and other hazardous conditions, interlocking the trains so that they don't collide. The next group of functions are automatic train operation, or ATO, which is mainly dealing with the roles and responsibilities that some of the drivers or train operators have to do, like moving the trains between the stations, regulating the speed, and some other functions like closing and opening the doors. And then the last group of functions are ATS, or automatic train supervision. This is mainly the back office, which is looking after the scheduling of the trains, making sure that the trains' movements are regulated for passenger convenience, and setting the routes manually or automatically. So these are the functions of the ATS. But automating the systems have different levels. Not all automatic train systems are the same. They go through different grades of automation, GOA 1 to GOA 4. And as you can see, as we increase the level of automation, the role of the driver or train attendant is decreasing to a point that we get to UTO operation, unattended train operation. That means that there is no one in the cab. Some trains even don't have a cab, and there's no one on the train, and the trains operate automatically. So which systems deliver which one of these functions? Let's take a look at the CBTC moving block system. CBTC stands for Communications-Based Train Control System, and that's based on a moving block. Taking a deeper look at this one, we need just to understand the conventional signaling system that has been in operation for over 100 years. How that works is that the track is divided into segments or blocks, and every block is equipped with wayside equipment and the signals. The train occupies minimum one block, so when the train is on one block, that is a red zone, along with the preceding block, which is the safety zone. So those two blocks are occupied with the red signal. The preceding to red zone is yellow zone, which is the slow and go, and then the rest is green. If you just look at the fixed block system, the top diagram shows that how the trains are separated based on the occupied blocks. And as you can see, the distance between the two trains on the top diagram is longer than the bottom one. Why? Because the bottom chart is not dividing the track into physical segments. It's a moving block, which is based on the concept of virtual blocks. So that means that the trains are separated based on the movement authority and the safe stopping distance and the safety margin that is colored in yellow. If you just want to look at the architectural diagram of this, the trains are separated based on the curve that you see as a green curve, which we call it movement authority. That shows the safe speed that the train should not exceed that, and the point that the train has to stop before colliding with the other train. This movement authority is continuously updated based on the wayside processors that obtain train position from the trains and do the calculation and pass the movement authority to the onboard computers on the train. And the train's responsibility is to ensure that they always follow the movement authority that they have been granted and do not violate that. Another key important factor is safe braking model. Every train, depending on its characteristics, it has a different braking curve. In addition, there are different factors. If there is a driver on board, the driver reaction takes time, the propulsion cutoff, the brake engagement, and many other factors, and the position uncertainty. When we take these factors into account, then it just shows us the safe braking model that every onboard train system has to follow the curve and do the calculation and make sure that at any point, if it is needed, it comes to a safe stop before colliding. Just showing it in a different way, you see two trains are following, and the The curve in yellow is just showing the movement authority, which is the maximum speed at the stopping point, which is right at the point that the green zone changes to red zone. As the trains move forward, the speed should be reduced, so does the extent of the green zone, and the red zone will be calculated all the time. Now, what happens when the front train takes the right turnout and then exits, gets out of the way of the train behind it? Now, all of a sudden, you see the movement authority, the yellow curve, is extended all the way to the train, to the next train on the same track. And now you see that the train can move at a faster speed, and the braking point is further ahead. So this is what is updated all the time, and these are passed to the train equipment. If we just look at the CBTC system architecture, this is a block diagram that the heart of the system is the zone controller, which is a vital system, and then you see that the wayside equipment communicate with the onboard equipment and also the central office. And data communication system is connecting all these blocks together. Each one of these subsystems have a role and function to deliver. The central office, which is mainly the ATS, Automatic Train Supervision, is a non-vital system that is looking after the train regulation and the schedule alignment, route settings, and so on. These are the functions of the back office. The wayside is a vital system that is a collection of processors that are continuously monitoring, collecting the information from trains' positions and their speeds, and they are just calculating the movement authority and passing it through the trains. The train board equipment, the equipment and computers on board the train, these are the ones that are taking the movement authority and making the decision that at what speed they have to move, and then calculate their position all the time, and then make sure that they can stop before the movement authority is violated. And the datacom system that is non-vital subsystem that is stitching all these subsystems together. Another representation of a CBTC system is just showing the ATS computers, servers, data loggers, communication with the wayside, and the wayside communication with the train equipment and the trackside equipment that help the train in order to determine its position. All of these are controlled through the control center. This control center is responsible for controlling the entire railway system, not just the train control. This is a representation of Guangzhou Control Center, one of the nice control centers I have seen. As you can see, this is controlling the trains, the power, the traction power, the SCADA, the fire ventilation system, the CCTV, the safety, security, and everything. What are the benefits of the CBTC that can be summarized? It's just increased safety and reliability. The trains per hour can be increased up to 40 trains if they are designed properly. Right now, Victoria Line in London operates at 36 trains per hour. TTC recently has come close to 27 trains per hour. So this is the number of trains per hour that can be operated. The system will be is bi-directional. The operation flexibility is high. The train arrival time is up to the second can be reported. There are green CBTCs recently are just taking some momentum in order just to ensure that the energy consumption is optimized or sometimes minimized if needed at a cost of ridership. It needs less crew or no crew on board, and the operating and maintenance cost is lower because it does not use as much hardware that the conventional signaling systems use. So this automation started back in mid-80s. In fact, the first CBTC moving block system was designed here in Toronto by a company you can see at that time. And then it was deployed on the Scarborough Rapid Transit, which right now is converting to subway. At the same time, same year, it was deployed in Vancouver. The same system, the only difference was that TTC in Toronto decided just to have a driver on board. Vancouver SkyTrain did not have even someone as attendant on board, and they have been operating for over 30 years. You see, the adoption trend in the industry, in rail industry, is very slow. Normally, rail industry is lagging behind the technology. It took almost 3 decades until the last decade that it has taken off. And as you can see, it's expected that by 2020, the number of automated systems will just increase, and over 2,000 kilometers of transit systems in major cities in the world will be equipped with automated systems, mainly CBTC. So that was one train control system that has been in operation for a long time. The next one that I will review here is the European Traffic Management System, ERTMS, which consists of 2 subsystems, ETCS, which is the European Train Control System, and GSMR, is the global system for mobile radio communication, and the dash is for rail. It's the spectrum that is dedicated for the rail. Before EU becomes united, every country had its own signaling system, their own rules, regulations, signal aspects were different, and sometimes some trains were just passing through many countries. They had to be equipped with multiple train control signaling systems so that they could just move through the countries. Otherwise, they should have changed the locomotives, or the passengers had to just change the trains. So the level 1 of ETCS, which was developed back in the 90s, it was just an overlay on an existing system. The train drivers, they still had to follow the line side signal aspects, and the tags or balises that were just installed on the train, on the track. The main reason for these balises or transponders on the track was just to communicate the information from the control center to the vehicles. At the same time, it was a point that the train position was calibrated. Anytime that the train was passing over one balise, its position was compared to what it was reading, and was calibrating its calculation. The onboard train control systems were responsible for calculating the speed profile and coming up to a braking. The next level of the ETCS went to the next level and started the communication directly between the vehicles and the control center through radio spectrum. So this would just allow the elimination of the transponder tags on track, but they just remained as the position markers. So each time that the train was passing over these, it was not exchanging information, it was just reading the position of the transponder to see whether it is aligned with the position that it has calculated. If there were any margin of difference, then it would just recalibrate that. So this one, the train-borne equipment was just loaded with the trackside characteristics so that they could just do the calculation and coming up with the train location and the train speed on their own. But it did not need any trackside signals anymore, so the trains could just follow the computer's directions. The next level, which is the level 3, it takes it beyond level 2, and the train integrity is handled by the onboard equipment. Train integrity is a concept in rail industry, especially when it comes to freight rail, when the trains are 2 kilometers long. So there are possibilities that the trains may depart. And then in order just to make sure that the train is still one piece on the front and the end of the trains are still accounted for the train length, train integrity function was handled by the wayside equipment. With level 3, that train integrity function is passed to the onboard controllers. So then it just, again, reduces the amount of hardware on the track side, because every hardware is cost for installation, maintenance, operation, and it just reduces the reliability and availability of the system. With the ERTMS, if you just take a look on the reports, this just shows the amount of rail track in kilometers and the rolling stock that have been under contract for installation up until end of last year. The track kilometers over 95,000 kilometers, and the number of rolling stock over 12,000 rolling stock is under contract for installation throughout Europe, Asia, and North Africa and Middle East. This is a representation of where ERTMS is being utilized. Mainly in Europe, followed by Asia, and then the rest of the world, with the exception of North America. We don't see that too much here. So what are the benefits of the ETCS? As I said, it just eliminates all the national train control and signaling systems throughout Europe. It just creates a seamless European operation and increases the competitiveness for the suppliers so that they can compete throughout Europe. And it's a standardized system architecture and function across Europe. And it just increases the traffic by about 40% at a very cost efficient. So if you have infrastructure and you can use it, increase the utilization by 40%, that means that you don't have to spend billions of dollars building the infrastructure. Although that has to be built in order just to catch up with the growing demand. But if you can increase the utilization of your existing assets by 40%, that's a huge saving that will just provide. So that's mainly the interoperability of these systems that were just important for the ETCS. And then it's positive train control system. As I started with that accident in California, which led into the Train Safety Improvement Act 2008. That was a mandate by the US government for all the freight and passenger train rail operators to equip their systems with a protection system to avoid similar events. Although since 2008 we have seen additional major incidents, but at least the system is being installed widely. The deadline for the industry in US was end of 2015 to install all these PTC or positive train control systems, but it has slipped until end of last year and is still continuing. Taking a look at the positive train control system, the main elements of the system is the train itself, radio communication, back office system, and positioning system. If you just look at the two key systems that are in operation, one is GPS-based positioning, which is IETCS, which is interoperable electronic train control system. And the other one is AXIS, for advanced civil speed enforcement system. The positioning system for AXIS is transponder-based, which allows for better positioning where the GPS may not have coverage, mainly in the tunnels and some other areas. So these are the two main systems, main products that are being deployed in the US. AXIS is more adopted from the safety perspective because it is a vital system type approved. IETCS is a non-vital overlay. What they do is that they just, again, provide audio and visual data to the train driver, which shows the train status of the signal, the position of the switches, the speed limits, speed restriction at level crossing, and work zones. The speed is the movement authority for this type of trains are also calculated by the central and trackside systems and passed to the train operator. So the train operator will see the train speed and which is calculated based on their existing speed, the length of the train, the weight of the train, and the grade and the curvature of the track ahead. So this is how the movement authority is calculated and passed to the train driver. If you look at the bottom right chart, it just constantly updates the information to the driver. The green area, it just shows the track profile, and it shows the safest speed that it has to move under, and it shows how many seconds it remains to come to stop. So that's the type of information that is passed to the train operator. Now, if the train operator ignores or misses any of these signs, then the onboard computers will just apply the brakes and bring the train to a safer stop before any incident. The key functions are delivered through different subsystems. The positive train control system architecture is, again, 4 subsystems. Back office segment, which is responsible for train dispatching and communication with other train operators. There are many railway operators, freight and passenger, commuter rails that are operating in the US, so they have to be connected and communicating through the back office system. The wayside segment that monitors and reports the signal indications, the switch position to the locomotive segment, at the same time to the back office. So in turn, the locomotive segment will receive this information and calculates the safest speed that it has to operate, and monitors and reports that to the train driver as well. And then the communication segment that connects all these subsystems together. Taking a look at the dashboard from Federal Railway Association, FRA. As I said, the deadline in order to implement all these train control systems were just, the deadline was 2015. It was missed. It was extended to 2018 because really FRA did not know what the target is setting for the entire industry in the US. Hundreds of railway operators, passenger operators. At the end of last year, they just reviewed the status, and this is the dashboard, which shows that in many areas they have successfully installed the system, with one exception that on the passenger track, 30% of the track mileage is installed with the PTC and is still continuing. The deadline was extended for only those that have done their part in order to demonstrate that they are moving in that direction. The others who have not, they may just be facing some restrictions in terms of their operation. So that's from FRA for dashboard. Putting all these together and comparing all these 3 systems leads to this chart. Automatic train control system, as I explained, it has 3 groups of functions. ATP, which is the foundation of the automatic train control system, is vital functions that are delivered by the equipment that is responsible for ATP. As you can see, positive train control in the US, its mandate was based on the 2008 Act, which was mainly to ensure that the operation is safe. So that's the scope of PTC, limited to ATP, although it can be extended to automatic train operation, but that's not their mandate. So that's what PTC is delivering. The next level is ETCS. If you notice, ETCS was mainly deployed because of interoperability. The train operation was safe in Europe, but they were not interoperable, so they wanted just to get this interoperability in place. So it is achieved in 2 stages. There's stage 1, which is ETCS, level 1 and 2, and then ERTMS, which is adding the radio spectrum dedicated to railway, which allows the additional throughput and connection of the subsystems, which can deliver the entire spectrum of the functions and increase the level of functionality of the European Railway traffic management system. Now on the left-hand side, we'll see the CBTC. CBTC, as I said, it started back in the operation back in the 80s. At that time, there were no rules, standards, regulations, or functional requirements how to develop it. One company started that, the other companies followed, and they developed their own systems. They all delivered the same function, but in isolation. So CBTC is not interoperable. That's one of the shortcomings of the CBTC. And in fact, the mandate of CBTC was mainly the short line transit transit lines, although right now we see that it is being deployed on freight rail in Australia as well. If you want to just compare these three systems from automatic train protection perspective, from automatic train operation, the possibilities of UTO operation, interoperability, capacity, and maturity. We see that CBTCs has a very high capacity for throughput. It can move the trains theoretically 60 seconds apart. But these days, the lowest headway in operation in France is 85 seconds. So trains are moving 85 seconds apart. So every 85 seconds, one train arrives at the station. So this is the high throughput for those who really need to move the trains as close as possible. ATC that is being deployed here in Toronto right now is in operation from VMC, Vaughan Metropolitan Centre, all the way to DuPont. That was commissioned last December. This is increasing the throughput. The rest of the systems is still being upgraded to CBTC system. It is expected that by the time that everything is deployed, there will be 30 trains in operation per hour. But there are some other factors that need to be taken into account. If there is enough rolling stock to move, if there is enough power. The traction power is also another constraint. That even if the CBTC allows you to move the trains that close, if you don't have the vehicles, and if you do have the vehicle, you don't have enough power, because you put a stress on traction power when you have, let's say, two more trains within the segment that was covered by the traction power substation. Now, that has to be upgraded as well. And the infrastructure, whether the zero speed restrictions or a bottleneck or not. So that's for the CBTC system. Looking at the ERTMS, as I said, the main objective was interoperability, which is the number one objective for ERTMS. The automation will be done through level 3. Level 3 is still under development. The deployment has been very limited at this time. The maturity of the ETCS at this time is low because it has not been in operation for many decades like CBTC, but it takes time for the maturity to climb up. And then finally, the PTC system, which the main objective was automatic train protection from safety perspective. The ATO and UTO is not supported, it was not mandated at this time. And if anyone can do that, that's open and above what you need. The capacity improvement has not been considered as part of the system. However, if you can increase the safety level and if you can operate the trains at a faster speed and safer, then capacity automatically improves. And from maturity level, it is still at the initial stages until the maturity is building up. So with this, I wrap up my presentation at this time and ready to take some questions hoping the next time that you are taking a subway, then you just think about how this subway is operating through the dark tunnels at the speed that you're operating. You're taking it for granted every day in, day out, not knowing that either the driver is in charge or the automatic system is in charge, how these systems have evolved over more than 100 years to get us to this point. Thank you very much. Yes.
Thanks for the presentation. I'm curious as to if you think there are any situations where on a subway network it doesn't make sense to implement an ATC system of some sort, if manual control makes more sense for whatever reasons.
As I said, if you don't need that high level of throughput and you have a system that the safety of the passengers are not in the hand of the train operator, that means that if the train operator passes a signal at danger, there are mechanisms in order to bring the system, the train to stop without violating the rules. And you don't need that throughput. Yes, you don't need just to spend too much money implementing automatic train control system for the network. Otherwise, if you need that, the only way is just to take the control from the driver and move into the system that automatically moves the trains as close as possible for you just to get the most out of the infrastructure built in place. Does that answer the question? Yes.
I'm really fascinated because I didn't know a lot of this. ATC, the term ATC is used a little loosely. I think it was used in BART and in Momato. Are those CBTC-based systems, or are they some previous generation before CBTC?
They are
and also who has CBTC now? Is it widespread across subways, or is it just here and there?
That's a good question. ATC is not limited to CBTC. That's the answer. Even with track circuits, you can deliver the ATC system. But with track circuits, if you want just to increase the throughput, that means that the blocks that I was explaining, you have to break that into smaller blocks so that the trains can move closer together. The moment that you just physically break the track into smaller blocks, that means that the wayside equipment increases substantially. It increases the cost of deployment, the cost of maintenance, and every single piece of hardware that you add, it just reduces your reliability and availability. So with the CBTC systems, because the wayside equipment is minimized, so the reliability and availability is very high. Because of the level of redundancy that is built into CBTC, the downtime is very low. And if it is built properly, Vancouver, the only downtime they had after 30 odd years was because of the traction power loss, not because of the train control system, which led into that big headlines in the papers 3 years ago, and the top layer of Translink disappeared because they were not maintaining the system properly. That was a CBTC system. For BART, the existing system is a home-developed system by Westinghouse decades ago, and right now that system is not supported by Westinghouse. The people with BART who were developing that, they have retired, so that's why BART has initiated a $1 billion program in order to deploy CBTC across its entire network. And based on the feasibility studies and analysis, it will just improve the throughput by 15% minimum. So that's the reason they are. In North America, aside from Vancouver, which the entire network is CBTC, Toronto, the Young University line, it is underway. New York is another big one. If you notice, I was just talking about interoperability of the CBTC. New York, back in the mid-90s, they started developing their own specification and asking the suppliers to apply for qualification. So 3 companies so far have been qualified for the interoperable interface specification, I2S, that has been developed by New York. and that's Thales, Siemens, and recently Mitsubishi. So these are the only three companies that they are qualified to develop and deliver systems for New York that are interoperable. But the way that they spend too much time on developing this, mid-90s right now is more than 20 years that they have been doing this. New York is facing a 50-year backlog in order to upgrade all their lines to CBTC based on the existing trend that they are following. And that's not acceptable. They are desperately challenging the industry in order just to come up with solutions that can just cut this time to something around 10 years. So that's one of the challenges of deploying, because CBTC deployment from the industry perspective is seen as taking too long. The average life cycle of deploying a CBTC on a system is anywhere from 6 to 10 years. So that's something that is one of the, especially on the lines that are in operation, because the track position overnight has to be shared with the maintenance crew. So if a subway is down for, let's say, 5 hours every night, then 2 hours will be given, let's say, to the new system implementation, and 3 hours for maintaining the existing system. That's why when it gets to excessive downtime, we have seen that for Toronto as well, weekend shutdowns. We always hear that, okay, this weekend subway is not in operation because the new system is being deployed. There are different approaches, big bang approaches. Some say that, okay, we shut the line for, let's say, 3 months. This is what Andy Byford, the former CEO of UTC, is introducing to New York, and is just facing a lot of challenges in the public. He says that if we just take the big bang approach, if we just, New York operates 24/7, and the maintenance is only done through single tracking and some small downtime. That's not sustainable. That's why we see that train systems and the train control systems that are not upgraded, some of them are over 50 years old, and they're still using levers in order just to move the switches mechanically. So that's a challenge for that. So that's the CBTC deployment in North America.
So WMATA is not CBTC?
WMATA did not have a good experience with CBTC. So some are saying that we regret it because we deployed CBTC. There are some cultural issues when you move from one system to another system. If there is no culture of acceptance, the system is doomed to fail. WMATA CBTC is not utilized to the extent that it should have. And recently they have called for some feasibility studies, what to do for that. Some are saying that the 21st century technology was deployed on 19th century system. So these are some of the side issues with the CBTC. But in Europe, it's widely spread. London, all systems are moving to deploy the CBTC. France, same thing. China, back in 1999, Shanghai only had 60 kilometers of subway. 2014, that is over 600 kilometers. It's all CBTC. Now, I'm not saying that everyone has to follow the same model, because there are differences in, let's say, for example, here, the politicians are still going around the circle, right? I don't want to get into that part of the discussion, but that's some of the issues that things will not be delivered the same pace that is delivered in Shanghai. So these are some of the issues.
Some new LRT systems have some aspects of automation, especially ones on running and for some sections on shared route of the way. So can you tell us?
Yeah, absolutely. This is the topic that part of the topic that I will be discussing next week in Jersey City. CBTC for light rail system is a good system, because CBTC is not all about automation. It's about protection as well. The Eglinton Crosstown that right now is under construction, I worked on that project for over 4 years, developing all the specifications for systems, including train control, and that's CBTC. Mainly because 12 kilometers of the right-of-way is in the tunnel, so that's automatic operation. About 7 kilometers is at grade, which is shared with the, not shared in the same of streetcars. It is semi-exclusive. So the cars, only emergency vehicles in some areas can get on track. The ATP, automatic train protection, is deployed across the line. So that means that the train driver cannot exceed and violate the maximum speed, cannot violate the safe train separation distance. These are the functions that will be enforced by the CBTC for the at-grade part of it. But going back to Edmonton Valley Line also has a CBTC system for train operation. The right-of-way is exclusive, although it is going through the streets, but there are level crossings and the bars coming down, blocking the intersection for the trains just to pass safely. Because that CBTC interface with the level crossing was not successful as it should have been. That means that when the train is just requesting the signal preemption to safely pass at the maximum speed through the intersection, if it is not getting the response back, it has to degrade the operation. And that just creates some interruption to the operation. If the train all of a sudden moving at 60 kph has to drop it to below 25, then that means it's interruption to the system. So that's the level of automation and CBTC deployment for light rail that we see. But Vancouver is also light rail, fully segregated, elevated right-of-way. Dockland Railway in London, that's also in operation for over 30 years. Very successful system, great separated, operated with CBTC, although there is an attendant on board, but that's a fully automated system. So there is room for CBTC deployment for the light rail. As a minimum, where it is shared right of way, is for protection of the system, not to violate speed and safe train separation. Yes.
I assume Via Rail is manual control blocks.
Yes.
The new REM in Montreal through the tunnel is going to be an automated driverless system like SkyTrain or something equivalent.
Yep.
But the KES and part of their planning have publicly said that the new Via frequent line that is coming through the North Shore would go through the same tunnel. So that means that same tunnel under Montreal would have automated light rail ICTS technology and manual control. I've been racking my brain trying to find, is there any place in the world that does that, or is there any way of upgrading the vehicle control system so that's feasible, or is this just, nonsense?
Okay, let me just explain a little concept here. TTC has over 70 types of maintenance vehicles that they have to operate throughout day or night in order to maintain the system. One of the major challenges was that do we equip all these 70 types of trains with the CBTC equipment? It does not make sense. Even some vehicles, they don't have enough space for the onboard equipment. So that means that the trains, the maintenance vehicles that are not equipped with the CBTC system, or the trains that are equipped but they fail to communicate, we call them NTCs, non-communicating NCTs, non-communicating trains. So there has to be a way for moving these non-equipped maintenance vehicles or non-communicating trains to an automated train control system with CBTC. It has a function that allows for manual route reservation, MRR, so that when the train is moving through the system, then it is detected. There has to be some secondary detection system in order to detect that this block is occupied, so that the CBTC trains are not allowed to move into a block segment. However, if the train moving through the system is violating the rules, then that would be a danger to the CBTC trains that are following the rules. So that's the part that manual operation and procedures become important. So now to your question, if VRL wants just to operate through part of REN, that MRR is one of the functions that can handle moving the trains throughout the automated system so that the CBTC knows that this piece of track is occupied, and when it moves, the next piece is occupied. So that's the, but if the number of these trains exceed a certain level, that would be too much interruption to the CBTC, to a point that CBTC trains get paralyzed.
Especially if they're operating at 60 or, well, not 60, but 120 seconds or
Exactly.
3 minutes.
Since you brought up the VRL, now Canada is caught between Europe and US. There are a lot of discussions, monthly meetings, that should we just take ERTMS from Europe or should we take PTC from states? And the experts are saying neither. We want to just take something that takes advantage of both and does not go through the same lessons that they learn. So we want just to develop our own Canadian solution. Yes?
Thank you for the interesting presentation. Just as you mentioned that the CBTC has developed for many years and it also has been applied all over the world, including China and European countries. And I just want to ask, do you think the CBTC is mature enough? And if not, what would be the most important developing direction for this system based on your personal experience?
Let me change my hat and just put my future hat on. I see a time that trains will be controlled through cloud. And that would be the ultra advanced train control systems using machine learning, artificial intelligence, and the emerging technologies for controlling the trains. In fact, right now in Australia, they have deployed some level of artificial intelligence, machine learning, that just shows the train moving through the tracks. It just shows graphically, just like the self-driving cars. That's the same technology is being deployed on the trains. The CBTC at this time, as I said, the constraint and the shortfall of that is interoperability. So let's say the reason that New York has a lot of problems with that, and they want it interoperable because it is just like a spaghetti. The network, if you look at it, trains are moving throughout a lot of lines. So you cannot say that this line has to be delivered by company A and this line by company B, and I don't need any interoperability between these two. Those chances or those cases are very low. Most of the trains have to be interoperable, and that's why they develop I2S for the industry in order to deliver the interoperable. That's the only shortcoming for the CBTC. Some are complaining about the time of deployment and the cost of deployment. It's true because if the line is stretching hundreds of kilometers, then CBTC may not be a good solution, although Australia operated the first freight rail deploying CBTC, a new level of CBTC so that we can just take advantage of the benefits of CBTC. But the next generation will be all cloud-based train control systems, interoperable.
Are there any other questions? Okay, well, thank you for a great presentation.